All right, let's take a look at some square roots and some Pythagorean theorem problems and see if we can get this figured out for you. All right, so first of all, we have something that we call perfect squares. And what perfect squares are numbers that you could get by taking a number and squaring it. So 3 squared is 9. So 9 is called a perfect square. 4 squared is 16. So what we really want to know are these perfect squares. If you don't know pretty quickly that list of perfect squares, it wouldn't be a bad idea to write them down. So when you get to your exam, or even if you're doing your homework, just write them down in the margin of the paper so you have quick access to them. The reason that we want to have quick access to them is because what we're doing is square rooting. Square rooting is the inverse operation of squaring. So it ultimately undoes the square. So when you see a square root, and it's this symbol here, and you see the square root of 16, if this is a perfect square under here, then it's going to come out as a nice whole number. Now, it's not always, but we're sure looking for that to happen sometimes. We like it when there's a perfect square because then it gets rid of that radical that's on there and it comes out as an integer, whole number. Okay, so just some vocabulary to start with. It says when a number is multiplied by itself, the result is called a, do you remember what I said? Hopefully you're thinking it's a perfect square. Okay, yes, it is a perfect square. But when I saw this problem, I thought, oh, let's go ahead and talk about some of the other things. And so, and really the main thing I want to talk about is this word radicand. The word radicand is the number that's underneath the radical. So in this case, 64 is the radicand. The actual symbol itself is called a radical. So just some terminology when you read it so you know what you're looking at. So before we even start calculating anything, let's just get an idea of sort of what's going on with this. So this one just wants me to estimate what I think in this example, the square root of 11 is. Between what integers does it fall? Because 11 is not in my list of perfect squares. It is not a perfect square. Oops, sorry. These. It's not one of these. But the square root of 11, well, think of just the number, the radicand 11, would fall somewhere between a 9 and a 16. Which means that if I take the square root of 11, it would fall somewhere between a 3 and a 4. And that's what they're wanting me to write here, that it should fall somewhere between 3 and 4. And if I calculated it, I could show that. I'm not going to mess with it right now. We'll do that later. But see if you can try that on this next example. What two integers do you think the square root of 79 would fall between? Again, 79 is not in one of my perfect squares, but 79 would fall somewhere between a 64 and an 81, which means that the square root of 79 would fall between 8 and 9. And that's what you'd write in the box or type in the box. It falls between 8 and 9. All right, so let's do some calculation with this now. So I'm going to start off with, well, I have 3 examples here. And the first one starts off, and it's actually pretty nice because you can see that I'm taking the square root of a 64 and the square root of a 25. Now, I'm not going to put that list of perfect squares on here every time. If you need to have a cheat sheet for a little bit, just jot it down on your notes paper or something. So looking at this problem, you have a 5, and it's being multiplied by the square root of 64. Well, since 64 is one of my perfect squares, the square root of it is an 8, because that's what I would square to get it. But that 5 in front is actually being multiplied by that radical. Plus 3 times, and now this time I have a square root of 25. That comes out nice also. The number that I would square to get a 25 is a 5. So that's the square root of 25. And then we just use our order of operations to kind of finish this up. 5, I got to do my multiplication first, so that's going to be a 40. Got to do my multiplication over here, that's a 15. And then I'm going to add those together. My final answer is a 55. All right, so now that was a nice scenario where those were perfect squares. This next one that I have a square root of 194. Now, they do get a little ambitious with the numbers, I'm not going to lie. So you may or may not know if 194 is a perfect square. So what you're going to do here, and remember that this course is kind of a tricky one because you do get to use a calculator for some problems and not for others. Well, for square roots that are not perfect squares and they're asking you to round to 3 decimal places, that's a clue that you're supposed to be using your calculator on that. So if you're using the standard TI 30X2S that you're supposed to have access to, because that's what you'll get on the test, what you are looking for, and I should have got a screenshot of this, it didn't cross my mind to do that, but you're going to hit, really you're looking at the 7 button. Directly to the left of that is your x squared. And what you want, if you'll see just on the calculator itself, not the button above it, but between those buttons, there's a little square root radical sign. So to get access to that, you have to hit your second button and then that. And if you do that, second and then x squared, you'll get that square root. All right, so what I'm going to do then is I'm going to get rid of that. So I'm going to clear that and start over because I'm just going to put this in my calculator as 53.46 subtract 2, and you have to hit times here, times, and now I'm ready for that square root. So I do the square root, so that's second x squared, and I put in a 194. Now, because I'm done, I can close that parenthesis that opened up or not. It just defaults to being closed. I press enter. All right, so hopefully, I know that's tricky when I don't have the actual calculator. Hopefully you have the same calculator. If not, you're going to want to know how to do these things on that calculator because that's what you'll have. It's worth a purchase. You're going to use the same calculator for several more classes. Okay, so 25.603 is what I got for that. Be sure to round appropriately. It counts it wrong if you round wrong. So the next number I saw on my screen was a 2. So that just means don't round up. Leave it. Okay, I got one more for us. This one kind of is a blend of those two. 100, I like it. It's a perfect square. The square root of 100 would be a 10. So I end up with a 3 times, remember that's being multiplied, 3 times 10. I was going to write it, and then I thought, oh, I'll do it in my head, and then I changed back. So 3 times 10 is a 30. So now I'm going to do what I did on the previous one. I'm going to go to my calculator. I guess you can always check. If I just do second x squared to get my square root symbol and type in 246, it does not come out as a whole number. So I know that that is not a perfect square. So you can always test it. Maybe you'll get lucky, but all right. So what I'm going to do then in my calculator is I'm going to type 30 plus 7 times, which is like looks like a little asterisk when you see it on your screen, times, and then I'll hit my square root of 246. So here I go. I'm going to clear it out. 30 plus 7 times second x squared to get the square root, 246. Enter. And I have a 139. I'm going 3 decimal places. That would be a 0.79, and it says 07, so that 7 here is going to make my O round up to a 1. And that would be my answer. Okay, so that's just a practice with the calculation of it on your calculator. All right, so one of the big places that you can use square roots is with the Pythagorean theorem. Very common theorem, very, very handy. And so the rest of this time I'm going to talk about our Pythagorean theorem. So first of all, the Pythagorean theorem developed by Pythagoras, and it deals with right triangles. And it only works on right triangles. So you've got to know that you've got this 90-degree angle here. And in a right triangle, it creates these 2 legs. Those are the ones that create the right angle. That other side, that is always going to be the longest side, and it's across from your 90-degree angle always. That has a special name. It's called the hypotenuse. Hypotenuse. All right, so given a right triangle, this theorem, Pythagorean's theorem, will always, always hold true. If you take this leg right here and square it, plus your other leg squared, it should always equal your hypotenuse squared. Will always be the case. The order you add here doesn't matter, so don't get caught up on is that A or is that B? It doesn't matter. They're just the two legs. But C must always be over here on its own. So here's an example that's asking us to determine whether we think this is a right triangle. Well, since Pythagorean's theorem always works on a right triangle, I'm going to test it with the Pythagorean theorem. So the two legs are 6 and 8. So you'd have a 6 squared plus 8 squared. And really what you're doing is you're saying, does it equal the hypotenuse squared? It's a question mark I put there. Does it equal? I don't know. I hate to say equal unless it does. So what I do then is I'm going to go ahead and test it and see. Well, 6 squared is 36. 8 squared is 64. Still a question mark. 10 squared is 100. So I don't know. Do you think is 36 plus 64 going to equal 100? Why, yes. Yes, it is. So it is equal. If you get it to work out where that's a true statement, then your answer is going to be yes. So let's look at our two yes options here. Which one do we want? Yes, because 10 squared equals 8 squared minus 6 squared, or because 10 squared equals 6 squared plus 8 squared. This one. The Pythagorean theorem has you add those legs, not subtract them. All right, so that's if you're just trying to see if you already have a right triangle. Let's actually say there is a right triangle and we can use Pythagorean theorem to find some missing sides. All right, so in this example, and man, I hope you're not watching this on your phone because to get these questions in there, they're so lengthy in the instructions. I guess it doesn't even matter. Here's what we're doing. We're going to use the Pythagorean theorem to find out the length of the hypotenuse in this triangle. So we can see they gave us the two legs. So they gave us A and B, and we're supposed to figure out C. So if I use my Pythagorean theorem, I'm just going to write it. More times you write it, hopefully you'll remember it. So A is one of the legs. Doesn't matter which one. I'll just say it's 9. So that's going to be 9 squared. Plus the other leg is the 12. 12 squared equals, and I don't know what C is, so I write C squared. Now on the left side, I'm going to go ahead and just evaluate that. That's going to be an 81 plus a 144. So now I'm going to add the two together, 81 plus 144, and I'm getting a 225 on that. Now, notice that I have now solved to get C squared, but I want just C. So remember what I said earlier, that squaring and square rooting undo each other. So if I want to get rid of the C squared and just get a C, then I am going to square root it. And the square root, the square, they cancel each other out, and I have C. But to keep my equation truly equal, I would have to do the same thing on the other side. I would have to square root it. All right, so if you do the square root, so that's back to your calculator, second x squared, and then you do 225. And what do you know? It comes out nice. That means 225 is a perfect square. Getting kind of big. You maybe didn't know that, but you got the calculator. It'll tell you. All right, so we found that the hypotenuse length is 15. Just as a quick check, remember that what I said, that the hypotenuse is always the longest side. So I always do a quick glance. Did my answer get, yep, it's the longest side. So just a little check you can do. All right, I made this picture a little bit bigger so you can see the triangle. The directions are just saying find the other side. This is a little bit different problem though, because notice this time, I know the hypotenuse. What I don't know is one of the legs. All right, still be in the habit of setting it up nice. I'm going to go ahead and write the formula. A squared plus B squared equals C squared. And fill in, I am looking for A squared. I don't know that. Now, B is going to be 8, so that's 8 squared. And C is 17, so that's 17 squared. Right, so A squared plus 8 squared is 64. I do not know what 17 squared is, so 17. And then, okay, this is maybe worth noting. On your calculator, instead of hitting second x squared, so I put 17, and then if you just hit the x squared, it'll put a little squared on your 17. And so that actually equals 289. Now we're going to solve this equation. So I need to get the a squared isolated. I want this by itself, which means this plus 64 I would rather not have here. I want that to go over there with the other number. So I'm going to undo a plus 64, and I'm going to move it to that side by doing the opposite operation. I'm going to subtract 64. A plus 64 and a minus 64 cancel, and I'm left with a squared equals, and 289 minus the 64 gets me a 225. And now my a is sort of isolated, but I still got that squared that I don't like, so I'm going to undo the square by square rooting. Square root. Do you know what the square root of a 225 is? Did you remember from the last slide? It's actually just a 15. So now we know that the leg is 15. Again, one quick check. The hypotenuse should be the longest. It's 17. That's longer than my 15 or my 8, so I'm good to go. All right, last slide here, doing Pythagorean theorem, but it's sort of like an application of it. You're going to have to draw your picture, and hopefully somewhere in your picture there's a right triangle. So looking at this, it says that you have a ladder that is 17 feet in length. It's resting on a branch of a tree. All right, so I'm going to go ahead and draw that. And I have my ladder. I'm just going to put it at the lower part of the tree, just like right here is my ladder leaning against it. All right, so it looks like this. There's my ladder. All right, now it tells me that the ladder is, what did it say? 17 feet in length. So that's 17 feet. And the base of the ladder, so that's down at the ground, is 8 feet from the tree. Okay, so we're talking this distance right here. That's going to be 8 feet. How high up on the branch is the ladder resting? So that's this. Do you see the right triangle happening here? Boom, there's a right triangle. And they want to know how tall this is. Now, do you think that that is your A or B? Doesn't matter, A or B. Is it a leg or is it the hypotenuse that we're looking for? All right, I hope you acknowledge that this is going to be the right angle happening right here, which means these are your two legs. I'll call it A. They gave me the hypotenuse this time. All right, we did one of those. Let's try this. So using your Pythagorean theorem, let's fill in what we know. A is what we're searching for. B is the other leg, so that's going to be 8 squared. C is the hypotenuse, 17 squared. Feel like we come across the same numbers over and over here. Didn't we do 17 squared a minute ago? Do you remember it? I'm cheating. Yeah, it was 289. I knew that. Okay, 289. Now you're going to subtract 64 to the other side. Sorry, let me sneak that in there. Subtract 64. Any guesses what that's going to get you? You think I could have found some problems that had different numbers? I don't know. All right, I hope by now maybe you know what the square root of 225 is. 15. Okie doke. So the 15 is what the height is. That's how high up it is. It's labeled in feet, and it's shorter than the hypotenuse, so I'm happy with that. And there we go. All right, so hopefully these few examples help you out, get through that and understand it better.